then the problems are explaining these results, that how we physically interpret, because we now every day we come to know much more about our own galaxy and also the extragalactic sources. So I thank my collaborators. Many of them were my students and some of them are here, and I won't be able to talk about 80% of their work. I can only mention about 10% or 20% of the papers, or even 10% maybe. So this is the picture. This is a picture of how a cosmic ray detector looks like in modern days. This is the Pierre Auger detector in Argentina. One of the students from here visited this site. They organize a school in cosmic rays once in 2 years. So this is very hard to reach this place. You have to change many flights, it takes many days. And these detectors are water tanks. So the extremely high energy particles, their energy is 10 power 20 electron volt. In fact, particles have been detected above 10 power 20 electron volt. So this detector has detected many particles of the order of 10 power 20 electron volts. So what they do, the particles pass through the atmosphere. Like this is a pictures diagram, this is a artist's visualization, that when a high energy particle comes through the atmosphere, it is interacting with the air molecules and they are producing many other molecules, and you see this shower. It is called air shower. So finally you have at the ground level so many thousands of particles. So this is what is happening in nature, and the same thing people model mathematically in computer by simulation. So here it's very hard to build these detectors because it requires many countries, expertise and of course money from many countries to build these detectors, but the same thing is done modeling mathematically, which the code the students run, and that code is also very hard to difficult. There are some people who develop them and then other people try to add for their work. So what are the interactions happening? These are basic interactions. Conventionally, whatever we follow, nothing no violation. If you don't violate any rule, then protons can interact with the protons in the atmosphere, in air, and then they can produce neutrinos and gamma rays. And protons can also interact with the background radiations. There are so many photons in the extragalactic and the galactic medium, and also inside the sources, and they can produce more neutrinos and gamma rays. And if there are heavy nuclei, there are heavy nuclei, because many of them have been detected by these cosmic ray detectors which I was showing you. So if there are these heavy nuclei are disintegrated by photons, and when they are photo disintegrated, you get neutrinos and gamma rays. So finally you expect lots of particles on Earth, and we do get particles, but the challenge is neutrinos are neutral and it is very hard to detect them because they are weakly interacting. And gamma rays, when they are very energetic, they are absorbed by the radiation background. Like TeV gamma rays are absorbed by infrared background. PeV gamma rays, PeV means 10 power 15 electron volt gamma rays are absorbed by CMB. So it is hard to get them on Earth unless the source is very nearby. So this is a neutrino telescope. This is called ice cube. It is built at the South Pole ice, where you get very pure ice, and there this ice cube detector is placed under the ground level, 2 kilometers under the ground level, and there are strings, there are photomultiplier tubes which detect the radiation, Cherenkov radiation from fast moving particles. So the neutrinos come, they penetrate the Earth, and then they interact in the ice, and they produce charged particles like muons, electrons, and muons leave a track, electrons produce a shower, and those particles are detected here. Interestingly, in the recent past, for last few years, ice cube detector is giving very interesting results. They are saying that there are astrophysical neutrinos. So when they detect astrophysical neutrino, they associate a probability that is it astrophysical, because there is lot of background, so they have to work on the background to reduce the noise, and then they have to understand that what kind of event. They label them gold event, bronze event, depending on the probability that it is an astrophysical neutrino event. And then they try to, then what other people try to do? They try to find out the source from where this neutrino came. The neutrinos are neutral, they should maintain their direction. But if it is an electron type neutrino and you are detecting in the ice cube with the shower, the electrons are producing, the shower is wide and it's hard to find out from where the neutrino came. But if it is a muon type neutrino, the muon tracks are more focused, they are more, they are not spreaded so much. So you can track better 1 degree, within 1 degree or 2 degree the directionality of the neutrino. Whereas in electron type neutrino, you may be, your error bar may be 20 degree and very hard to see, because if you look at 20 degree of the sky, you can see many sources, then from where did it come? So then people try to go back to the catalogs of sources. There are various kinds of astrophysical sources like active galactic nuclei. So is there any source within that patch of the sky? Then was it in a high state at that time? Was it emitting lot of photons in different energy bands? So was there a flare going on? So people try to associate, but it has been seen that whether it is a flare or whether it is a quiescent state of the source, neutrino can come. And people have shown why, that even if it is a quiescent state, and during quiescent state the neutrino flux may be low, but the time integrated flux, if you take the time duration for a long time, that may give you a few events, because it is the time integrated flux. So whether it is flaring or not, if there is a source, neutrino can come. By source I mean it could be active galactic nuclei or gamma ray bursts, which happens for a short time. So these are the speculations and ice cube results people are trying to explain at the moment. Now, this is again the picture of neutrino telescope. So this is like when a neutrino, a muon passes the light, the Cherenkov light, the photomultiplied tubes detect. It shows it looks like this. Now this is another telescope. It is under the water. It is in Mediterranean Ocean. It is also underground 2 kilometers below, and then people are building up neutrino telescope to detect astrophysical neutrinos. It is not yet started. It will cover another part of the sky which ice cube cannot cover. This is a picture, it is not a real detector, so it is an artist's view. So those ball-like structures, these balls are like the photomultiplier tubes. They will detect the photon, the Cherenkov radiation from the fast-moving particle.
So what's the difference between this and the ice cube? So, is it similar in the, in the nature of the detector?
Nature of the detector is similar. There one is using ice, here water. That is the difference, and they covering different parts of the sky.
Ice is very pure.
Yes, ice is very pure.
Water you cannot get.
I don't know whether that pure or not. They have gone to this very deep level. I mean, they are going near the bed of the ocean. Okay. Looking, see, they cover a certain angular, they have angular coverage, and the efficiency depends on that. So there may be arc skimming, like they are coming from the other side, there may be coming near the horizon, but the effective area they have to calculate, like how efficient is the detector in different directions. For that they do a simulation that in this, if the neutrino is coming from this direction, my chance of detection is this much. So they associate, that depends on the area or efficiency of the detector. Not? So there is no ice here. They are using the Mediterranean Ocean. Because ice cube cannot cover some parts, some sources. There are sources whose positions, declinations are such that, because ice cube is located at the south pole. So it is mainly covering the northern hemisphere.
Okay, so sky view.
Yeah, so the neutrinos which are passing through the earth from the northern hemisphere, you can detect them well from the southern hemisphere, the south pole. And the passing through the earth is needed to reject the background. So you have a lot of background of muons. So you are trying to stop them, the background. So that's why the passing through the earth is needed.
How can you tell whether something is passing through here or not?
Yeah, directionality. Because it is at the south pole, so the neutrinos are maintaining their directionality. Neutral particles. And the muons are very high energy. Basically, you are taking the neutrinos which are interacting near the detector. You can see the interaction. So you know the directionality of the neutrino. And say you have said it's coming from this direction. So that's why this kind of study cannot be done with charged particles, cosmic rays. So it is hard to find the sources of cosmic rays because they are deflected by magnetic field. You cannot find from which direction they came. That's why neutrino astronomy is very important and gamma ray astronomy, so that you can find the direction. So this is another picture like I was telling about under the sea what is happening when a particle, when a muon is coming, suppose. The muon is produced by the interaction of the neutrino in the sea water. So it will pass through the detectors. The detector will register the Cherenkov radiation, the ball-like detectors. So now I am moving to the give you an overview of the gamma ray astronomy, because this field works with the information, the components we receive from different fields like neutrino, gamma ray, cosmic ray, it could be gravitational wave. So I was telling you about neutrino detectors. Now I am telling about the progress in the gamma ray astronomy, because Fermi-LAT was launched. Fermi-LAT is a detector. It is a gamma ray telescope. It is in space, and it was launched in 2008. That time its name was different, GLAST, but later they changed the name. So it has revolutionized the field of gamma ray astronomy. We knew very little about the gamma ray window, but because of Fermi-LAT, now we know much more. Fermi-LAT has seen lots of gamma ray emission within our galaxy and outside our galaxy. They have seen structures, extended sources or point sources. They have seen flickering, many flares. They have explored the dynamic sky. So within our galaxy, you see the magenta ball-like structure. Those are the Fermi bubbles, a bubble-like structure they have seen. Their diameter is almost 10 kiloparsec. This is the galactic plane. On both sides, this spherical structure. This is the gamma ray emission. They are seen by Fermi-LAT. Then other sources, many supernova remnants, then pulsar wind nebula. There are different kinds of galactic sources that they have seen. And then extragalactic sources. Almost every month or once in 10 days, we see a flare in active galactic nuclei. There are so many flares going on. Fermi-LAT is detecting them, and it is publicly available, so we can use the data from here, which is not possible for other detectors. So everyone can work with this data. And here our students extensively do use this data from this telescope. Many people have done their thesis, PhD thesis using this telescope's data. We study the time variability, how with time the AGN are showing flares, what could be the physical mechanism of these flares. And then many other detectors will come up soon. So this is the launching of Fermi-LAT when it was launched in 2008. Now this detector is another gamma ray telescope which will which will make a lot of difference in the next few years. This is the Cherenkov telescope array. This is under construction and also started taking some data for their calibration. It is situated in La Palma Island in Spain. So Cherenkov telescope array will have much better angular resolution and time resolution to detect the very low photon flux or any dynamic flickering or dynamic behavior or dynamic sources. So people are waiting, and India is trying to take part in this telescope in collaboration. But so far we have not got any approval from the government. Many institutions together are trying. They submitted a proposal to be part of this collaboration, because almost all countries are part of this Cherenkov telescope array collaboration. Basically, in India, the gamma ray astronomy manpower is very low. In this field, no one almost works in India. So that is why it is very hard for India to take part in any of these big collaborations. So now I will talk about how we look at these sources. Like there are various, as I was telling, that there are various kinds of sources. AGN, these galaxies whose centers are very brightly emitting cosmic rays. So these are our main targets. They are often observed and they are often studied also here in RRI. And gamma ray bursts, many people work on gamma ray bursts. They are emitting very high energy particles for a short time. Recently, there was a gamma ray burst. It detected very high energy gamma rays. So far, such high energy gamma ray emission has not been seen from GRBs. So some students are working on that from here. So these what are their density, how they are populated in the universe. So this is basically how frequently they are located and what is their luminosity. This plot basically gives that. So you can see that how easy to see them or how difficult to see them. Like this AGN, suppose that their number density is like that, but they are continuously emitting. But if there is a burst, it is for a very short time. So if you can catch it during that period, you get some data. Otherwise, you cannot talk about much, because when you try to understand some source, you need data in all wavelengths, radio to gamma ray. Otherwise, you cannot model that source. Every bit of information help you to constrain the parameters in the modeling. So there are starburst galaxies, there are tidal disruption events. So there are various kinds of sources. People try to understand them, whether they can be sources of high energy neutrinos. Of course, gamma rays are also detected for them. So as I was telling, that cosmic rays are deflected in magnetic field. So directly we cannot probe them, we cannot know. So it is
galaxy clusters. So is there sort of a redshift this thing, or
redshift distribution is also there. So this is per megaparsec cube. What is their density per megaparsec cube?
okay?
And this is their effective luminosity on the average.
Yeah. So what are the furthest sources? In other words, with many of these things, including high energy cosmic rays, there's sort of ultra high energy. I forget whatever they've got this acronym that there's associated with them. But some of the things that people in, doing alternatives to quantum, to GR and alternative approaches, they often are very interested in these ultra high energy cosmic rays.
Yeah.
UHCR, I guess.
UHCR.
Yeah. And one of the things that has always been curious is whether they have a certain stochastic, if there is a stochastic background that you have of this, or they can come, is one able to pinpoint that the furthest redshift from which these things come? I mean, that's perhaps
So far there are some observations like Z equal to 8 or so 7 for GRB and AGN. I don't remember exact values. The people have gone to optical emission, optically detected sources, farthest AGN or farthest GRB you are saying.
But they are not isotropic. They come
course
from
not.
very specific sources.
And I am saying there is a distribution, right? So these are extragalactic sources, they are isotropic distribution. These are extragalactic sources, AGN, GRB, and they are isotropically distributed. But there is a redshift distribution also. The farther the source is, it is hard to detect because you don't get much photon from it. So so it is, as you go away, of course your detection, chance of detecting something is very remote.
So this distribution is not intrinsic.
Not intrinsic, yeah. Not intrinsic. And
On the source, it's what we see on the this distribution.
so there is a redshift distribution. It is not that it is uniform. Now, what I was going to tell is that our objective is to find out the sources of highest energy cosmic rays. So we are trying to probe with neutrino and gamma ray astronomy. Now this is the current situation in the field of gamma ray astronomy, that there are various detectors which are, as I was saying, that they are going to up to very high energy, like 10 power 9 MeV means 10 power 15 electron volt, or 10 power 8 MeV means 10 power 14 electron volt. So this LASSO is the full form is Large High Altitude Air Shower Observatory. It is in China. It is giving very interesting results. So we look forward to LASSO results these days because they are detecting sources with gamma ray energy 100 TeV, even more. So most of these sources are within our galaxy. We never knew so far, I mean before last couple of years, we didn't know about that there are 100 TeV gamma ray sources will be detected within our galaxy. So it is so surprising, and people are trying to model those sources. That basically a very interesting thing is seen, and there are many workshops going on this topic currently, that in our galaxy there are many gamma ray sources which are emitting gamma rays up to 100 TeV, and there are halos around them. So what they are saying is the emission from a big halo. So how this halo is produced around the sources? So that the diffusion, you know that the particles diffuse in the medium. The diffusion is very different near the source and away from the source. So our galaxy is so complicated. Sometimes we see charged particles are trapped near the source because the diffusion is different, and that's why the halo is produced. Now people don't know the physics of how this trapping is happening near the source. So this is now a very hot field. Separate workshops are going on, and one of our students are collaborating in Spain, and so they are also working on these sources, the halos. So they have dedicated workshops on this, understanding the physics of halos, how the halos are formed around sources, and how the diffusion is changing suddenly, what causes trapping of cosmic rays. They are saying they are mostly pulsars, and around them there is a emission halo, like pulsar wind nebula. Okay, and whether they are pulsars, that is also not known, because sometimes we see there are supernova remnants also. So it could be pulsars, it could be supernova remnants. I am coming to that. How halos are formed, it is not unique, and you see, you cannot see halos in other galaxies because the emission is not so bright, and you cannot detect 100 TeV gamma ray from other galaxies, very difficult. So these things you can know only by detecting sources in our galaxy. So our knowledge has just started. So we are trying to understand. You want to ask something?
No, is it connected to magnetic field, because
Lot of things, magnetic field, like what happens when the first question people ask, suppose a source is emitting a very high energy particle. What do you expect? to just fly away from there, right? It should leave that place immediately because it has so much energy. It is moving at the speed of light almost. So why should it be there and emitting radiation? So what is causing the trapping? That I see a halo of 100 TeV gamma rays, and for that I need a 1 PeV proton to create that a very high energy electron. Then why is it not flying away from there? Why is it trapped there? The first question is this. Then people try to explain that there could be some instability in that region, plasma instability, which is trapping the particles. But these are still not yet fully understood. What is causing trapping? And this is the first time you are seeing something at 100 TeV, and you are saying such high energy particles are trapped. Okay, and another thing, that when you see a halo, you try to find out which sources are there. Is there a pulsar? Is there a supernova remnant? Something we know already. But sometimes it is seen that nothing is there. In a few cases, it is seen there is nothing. So we wrote a very interesting paper on this. There is a VSP student. So we wrote a paper that suppose you don't see anything. They have reported such results that we see 100 TeV gamma rays, but we cannot associate with any pulsar or any supernova remnant which is alive, which is emitting in other wavelength. We can bright. Otherwise, how such gamma rays can come? So we gave a speculation that it might happen that many thousands of years back there was an explosion, just like supernova explosion. After a supernova explosion, you see supernova remnant. But suppose there was an explosion which is not as strong as a supernova, bright supernova. So the remnant is very faint, you cannot detect it now. But if you calculate the emission from that explosion now, the explosion happened suppose thousands of years back, and I calculate the radiation now, it is possible to match with LASSO observed. So this could be one speculation. When you don't see say optical emission or X-ray emission, and you see that there is a very high energy gamma ray emission. So this is just a speculation. People are speculating a lot of things to try to explain the current situation. You want to ask something? No. So
what's the kind of localization for LASSO?
It's very bad. Ognipo can give the data, right?
Say pulsar nebula and supernova in the same region, you cannot sort of, distinguish between these sources. And there are a lot of cases in which pulsar nebula and supernova remnants and molecular clouds all are just supposed within the same bright halo region. So resolution is pretty bad.
Okay, thanks.
So now if there are halos in our galaxy, there must be halos in other galaxies, which we cannot see now, but someday they will be visible. Now, if there are so many halos, then they must be producing a gamma ray background, which we still didn't know that this could be a component in the gamma ray background. This could be a major gamma ray source at high energy. Although, so this is the beginning that we have seen in our galaxy. Now we are trying to understand how they are produced, and then if they are also present in other galaxies, what are their net effect to the gamma ray background. So these are on the farthest side, at the highest energy, you see the detectors, LASSO and HAWK. HAWK is in New Mexico. Is it in Mexico, or? I think it is in Mexico. So these are the detectors people are just looking forward to and the CTA, which will really add much more to what already Fermilab has given.
Where does MACE fall in this? The VR telescope?
MACE is the MAC, this ice cube or Indian.
VR MACE.
Devanjan was there, but I don't think anything promising is, I don't think people are talking about anything. So this Devanjan is involved in that. Yes. Okay, so here some students are working on galactic sources, and some are working, mostly we have been working so far with Fermi-lab data, extragalactic sources. But since LASSO data is coming up, a lot of people are interested in that. But these are not publicly available. Until they publish their paper, you cannot do anything with that. LASSO, yeah. So again, I was talking about the sources, that we have this map, this always in our head, that what is the size of the sources, what are the magnetic fields inside the sources, so that we don't confuse. As I said, that I am looking at the patch of a sky and I see many sources. Which it can be? Is it a galactic source or is it an extragalactic source? The galactic sources have much smaller size. Extragalactic sources.
This earlier plot, like you had all these detectors, right? Yeah. So this sensitivity large is better, right? Or
sensitivity is lower.
Lower is better.
Because then it is the flux, arc per centimeter square per second is the photon flux. The lower is the flux you can detect, the detector is more sensitive.
Okay. So this E astrogam. So like most of the other detectors have a similar sensitivity as a function of energy plot, right? There's a minima and then it just goes.
Yeah, it is going up. Why?
Yeah, so why is it so? I mean, that seems slightly different from these other ones, right?
So here there is a deep, I don't know why it is, because this detector is extremely important because it covers an energy range others cannot.
Okay.
Do you have any idea why is it? No. So this is very important detector, because you can see this is a gap. There is no detector here to cover this energy range, 1 MeV.
Location or whatever in which some seismic noise or something is so much higher. So you end up having, so it must be to do with some very specific detail about the, that is true for LIGO, for example. The range depends very much on the fact that it's ground based with specific, seismic noise, all of that has to be taken into account. And then you have some sensitivity range. And then if you take it to the space-based one, then the frequency range is completely different.
Yeah,
so
for most of them, it's like a similar thing.
Sanjeev, I don't know about this instrument, but one possibility is that this is in tens of MeV range, right? MeV is the most difficult of all astronomy branches. Okay, below 10 MeV, you are probably using Compton scattering, so you do not have any way of collimating the photons, but you are using Compton scattering, so angular resolution is extremely bad. That may be causing low angular resolution and therefore overall sensitivity also low. And above certain energy, you depend on pair production, and then your angular resolution improves.
Yeah, because
so
on they are also following like this.
So on two sides of that peak, you may be using two different physics for detection. I'm not sure, but that could be.
So you're saying like if you assume in the low energy, if you assume the quantum streaming as a simulation to get the sensitivity, you get this kind of sensitivity in low energy.
Maybe.
See this. So the Cherenkov detector basically detects a light flash from the Cherenkov shower. So it's all actually a light detectors, and they probably have a range of detectors, right?
But this is not Cherenkov range. This one is only at about 10 MeV or so. Here it would be pair production. So below 10 might be Compton scattering. Above 10 might be pair production. So those two processes give two different sensitivity curves, and that's where they meet.
But then you also said COMTEL, whose sensitivity is not very high, but then it can.
So you can see COMTEL and these are almost similar nature in that way. COMTEL was flown on Compton Gamma Observatory 30 years ago.
This one's bump was matching that one's dip.
No, COMTEL was only Compton. E-grade was okay, so that explains. COMTEL was Compton scattering telescope. E-grade was pair production telescope on Compton Gamma Observatory. Now, if you make a larger E-grade, if you make a bigger COMTEL, its sensitivity come down. Those two together might be
It's almost time. I should go. Saurabh is waiting.
No, but we are all asking. That's the point. Ask him many questions.
So this is the cosmic ray spectrum, ultra high energy cosmic ray spectrum. 5 minutes. So yeah. So this is the ultra high energy cosmic ray spectrum. So you can see these are the particles detected near 10 power 20 electron volt. There are large error bars, but the flux is like that. So this is the cosmic ray flux. Now the composition of cosmic rays and the slope of the spectrum is changing with energy. So, and these particles are charged particles, so they don't maintain any directionality. So you cannot probe them directly, so you have to understand from where they came. Then the only way is to use neutrino or gamma ray astronomy to figure out from where they came. Now, here we were doing, some students did their work on understanding the origin of these cosmic rays. They did, I was saying that the artist's view that the air shower is happening like rain, and same thing is happening in modeling. So his thesis was modeling these cosmic rays. So using simulations. When you do the simulation, you have to take into account a realistic picture. What happens when some particles pass through the ISM, magnetic field, radiation background, fragmentation, photo disintegration, everything you will have to incorporate. There are programs available, but there you have to fine tune it according to your problem. Then, so this is the modeling part. So Shaikat did his PhD on this in this ultra high energy cosmic rays. So that time we were doing a lot of work related to this. The simulation was running here in RRI, and he did his work well. Could finish here his work with finding out what could be the different populations of sources, how to explain the composition. We are not the only group. There is a bigger group in DAISY, and we are only 2 parallel competitors, I can say. So there is a big group in DAISY who does this kind of work, and Shaikat has done similar kind of things. So when cosmic rays interact, then they produce neutrinos. So is it possible to detect those neutrinos? That neutrino flux is too low, and we see that even the biggest detectors, which will be coming in up near future, for them also finding out this neutrino flux is very difficult. And then we came up with what can happen. Like there are many parameters when you do the modeling. As I said, you need a realistic picture. So realistic picture, then you have many parameters. How do you optimize them? This is a big task. So you have to run your code. You have to vary simultaneously many parameters. As many freedom you have in your code, as the longer it will take to optimize, and then you have to figure out what is the best fit in your results, both composition fitting and spectrum fitting. No, like depends on how many branching is happening in the interaction.
Okay, so this single line comes, and then they can become multiple lines, and those multiple lines again, each of them can again branch.
Again, electrons can do synchrotron.
I understand. Like, but if I just don't look at whatever the physics behind, and if I just make a stochastic model saying that few parameters model saying that okay, you have these branches, and at some rate they branch.
Then you are approximating. You simulate with 1 lakh particles, and then you find out.
No, because anyway, probably even if your simulation also, you do not know which thing is hitting what, right? So
no,
my question was, will the stochastic model be so bad that, I mean, it will not give you anything?
See, pen and paper calculation was done decades back.
Okay.
So now you cannot give anything. People don't take you anymore. So that what we used to do when I was doing PhD, suppose, that time already people started doing some Corsica, and we did pen and paper calculation, but now it is not possible to survive with.
But no, the point is that what is the mechanism? So you have a line
Yeah,
and
you
it
have to
becomes
attach
multiple
some
lines.
probability, like what is the probability of interaction.
So exactly. So now if I say that with certain probability, the single line becomes multiple lines, again each line moves independently, again they become multiple lines.
But that is there can be various kinds of integration. Suppose, as I said, some proton-proton interaction.
So I just put it in as a rates. Then what is the rate at which this single line becomes multiple lines?
It's not just lines, they're also colored.
Yeah, yeah.
Depends on the particles. So there's, so I mean, what you're asking is.
Can I just build up a stochastic model? Yeah.
That is the initial stage. That's why how they started.
Yeah.
In the earlier books, they gave those models, particle, how they can happen. Like there's a book by Geisler, he gives the similar kind of things what you are saying, equations. So that is the starting point. So then people build up these simulation codes.
But then this
Those are very approximate.
But then simulation code does what? You actually say that this guy is coming and hitting something else?
Hitting something else. Suppose I have
what
a
is
source.
the mechanism of this single line becoming multiple lines?
That is the interactions.
So I know, but that happens with some probability, right?
Yeah, but my medium can be different. Magnetic field can be different. My density.
Yes. So each time you will get a different answer, right? So that. So exactly. So that's then you can have a probabilistic model, right?
No, but I think that is, in principle, that is, I think, what is being.
That is the initial stage. What you are doing, people have done already that.
The calculation of those probabilities is done using quantum field.
That's fine. Yeah.
That's all.
Yeah, that's okay.
And that's more complicated because each line has different colors.
Yeah, yeah,
and you're doing it.
yeah. That's
But I think that's essentially what would be done.
okay.
It is Monte Carlo solution.
Yeah, that was the question.
Yeah. So finally, you have to optimize many parameters. Like we keep on changing the magnetic field. We don't know the magnetic field structure in the extragalactic medium, or in the galactic medium. There are models. So one has to play around the models with the magnetic fields. Suppose I see some emission from some protons of 10 power 20 electron volt. It depends on the medium, the magnetic field structure, the distance of this source, what is the coherence like, magnetic field is changing in between. So all these things are taken care of in the simulation.
Simulation does use Monte Carlo.
Yes.
Okay, so then that's basically, that's it.
Yeah. So basically, so suppose if we think that there is only one population of sources, this is a result of Showcasing study. That if we see that there are only one population, assume if we start with one population, then low luminosity GRBs can explain the ultra-high energy cosmic ray emission. If we think there are two populations of sources, then active galactic nuclei emitting pure protons and tidal disruption events emitting heavy nuclei can. Basically, what is seen that at the highest energy, the particles are not protons, they are heavy nuclei. And heavy nuclei cannot come from high redshift, because before they reach us, they will be disintegrated. So something must be there near us, which are supplying heavy nuclei at 10 power 20 electron volt. So that is why it may not be one population. There may be sources of protons, there may be sources of heavy nuclei, which are more closer to us, and those heavy nuclei, that's why those iron nuclei can survive and reach us. So this is one thing, but I have studied so far that some people did the study of ultra-high energy cosmic ray, and lot of students have been doing this multi-messenger astronomy with the multi-wavelength data, like the archival data they take in radio optical, and they analyze formula data, Swift data, and they then do the multi-wavelength study. So lot of students here like Raj, Obhik, I'm missing their names, Sandeep and others, Ognibo has also done. So lot of people have used multi-wavelength data to model their sources. The aim is basically you use the data in modeling in understanding how the emission is happening. So there can be electrons which are doing synchrotron, which are doing inverse Compton. There can be protons which are doing PP interactions inside the sources. And if you include everything, can you explain the emission? If neutrinos are detected, Can you combine this with the existing picture and say that yes, this source has sufficient luminosity to emit the neutrino? So I go back. As this is galactic cosmic ray, very exciting results. I don't have time to tell, so I go to the last slide, that UHCR sources are not yet identified. So the goal of multi-messenger astronomy is to identify the UHCR sources which are not yet been identified. Sources of astrophysical neutrinos are yet unknown. These may be AGN, most likely they are AGN. We don't know whether GRB can emit. Who knows? There can be many other sources, tidal disruption events, people are saying it can be. So basically not known. Acceleration mechanism not understood. There are various kinds of sources, and gamma ray universe is bringing us surprises almost 2-3 times a month. We can see some interesting paper which have unusual results, and there are many questions to answer now because of these results. Okay, I stop here.
Thanks, Nayantara, for a nice talk. We have time for a few questions.
Just to do with these very extreme energy or grand ultra high energy sources, I don't know what that is, but is there any sense or indication, since the sources are not yet identified, you say that, but I mean, at least in the TeV range, you said it's very clear that they're within the galaxy.
Some of them. 100
I'm
TeV.
really curious about this because I mean, these are potential sources for, early universe cosmology,
Yes.
right? So signs, I mean, the CMB is of course telling us a lot, but then anything, neutrino information also of that sort is very, very useful in constraining early universe scenarios. So in that sense, is there any idea whether there can be a stochastic but very high energy? I mean, they obviously have to be very high energy to reach all the way from very high redshift. Is there any sense that these could be in this ultra high energy range?
Which one?
Stochastic from the very early universe?
Because
or is it just
the
very
event
local?
rate is so low, if the ultra high energy event rate is very low and they cannot reach here from far away, which kind of particles you are talking about? Gamma rays? Gamma rays will interact with CMB and radiation background. Neutrino event rate is very low. Yeah. Yeah, that is.
Momentum space diffusion processes that happen. So these are things that people have, scenarios that people have proposed.
Yeah.
But I was just curious what the state of the art is on those high energy.
Yeah, so the Lorentz invariance is one possibility, that violation of Lorentz invariance, they can survive without doing the interaction. So as I was saying that the GRB happened recently, very high energy gamma ray, and people are putting new constraint on the violation of, the limit on the violation of Lorentz invariance from that.
I had a question. So are there any studies where different detectors collaborate for the directivity? So if we have something at the South Pole, so the northern hemisphere will be the field of view, and another detector at some, so they can detect.
That's what, that is the goal. Like the Cherenkov telescope array, there is a location in northern hemisphere, another one is planning southern hemisphere. So to cover the entire sky.
So just like the LIGO experiment, they can use it as a directivity method.
Yes, they are working together. All these detectors are working together. I think LIGO is also there to cover the simultaneous observation of events.
Yeah.
Such collaboration also happens for TXS creation, right?
Yes, TXS also that. So among the detectors there is MOU. They don't release the data because their papers come out together. Many collaborations. Okay, Saurabh can take over.
Okay, thank you once again.